Okay, so can you see the slides and can you hear me? Yes. Good. So now I have to introduce and grab my water. Yeah. So it's my pleasure to introduce our first speaker today for the hybrid session in the morning, and that is Jing Liu from University of Alberta. And today is a very University of Alberta intense day. So we have several, and I'm on the wrong page. And Jing Liu is an associate professor in the Department of Chemical and Materials Engineering, and she is an expert in electrochemistry, corrosion, materials engineering. And we will today hear about supercritical CO2. Yes, so one of the new or greener energies that we are trying to do in the world in order to combat the climate crisis. And this is very, very important in Alberta, so there has been a lot of research here, and we will hear more about it. Thank you. Thank you. And you get my microphone. Good.
Well, thanks, Yolanda, for the introduction. Good morning, everyone. I hope you all had a wonderful first day. So now today is the second day. Well, I'm Jing from Chemical and Material Engineering at University of Alberta. So before we get into the supercritical CO2 corrosion, let me first introduce us. Where are we from? Is it okay?
Yeah, it's good.
It's good? Yeah, there is a tag there, but it's okay. So our campus is surrounded by North Saskatchewan River. It's actually very beautiful even in the winter. Although it's cold, but you get to see all the snow view. Well, it's kind of similar setup like UBC. The UBC is surrounded by ocean. I got my degree from UBC. So this is our building. So this is our building. Most of the engineer, student, and office are here. And my office is facing this side. So I got to see all the good view. So you could tell, very important. And this building is our lab. So they are connected, chemical and material engineering. We got this new building in 2015, and it was built just between the chemical engineering and the parking lot. So actually, the university doesn't support us to build a new building. But then our former dean was very smart, saying that this is not a new building, we're just building an extension. So we got this thing here. Currently in my lab, I have 3 labs, mainly focusing on high temperature corrosion, hydrogen lab, and electrochemistry lab. And we got 18 members because I'm on maternity leave, so I got more postdoc than PhD student. I have 8 postdoc, 7 PhD student, and 3 master student. So they are here. Some of them are here. Those 3 are my student. I forced them to come here, otherwise, I don't want my talk to be empty. Now, a general idea of what we are doing. Yes, we are mainly focusing on corrosion and electrochemistry, but I divide them into 3 categories. The first one is we call it the technology pathway to sustainable energy sector, where we try to repurpose. So we repurpose the current refinery. For example, we repurpose the current refinery, not just cracking petrol crude, but also crack biocrude. So blend a little bit of bio oil with petroleum. And also, well, today's topic, we try to repurpose the current natural gas pipeline to transport CO2 or to transport hydrogen. Currently, article, they are blending a little bit of hydrogen into the natural gas pipeline, I believe 5% also. And as always, corrosion is an interaction between the material, the metal, with the environment. If the environment is too aggressive, we will think about it. Can we develop new alloys? So the second category of our research, we focus on alloy development for harsh environment. And we also do quite a lot of general corrosion research, because this is Alberta. We got quite a lot of interest in oil and gas related corrosion problem. So get back to today's topic, is we are focusing on repurposing existing pipeline and enhance oil production well for CO2 transportation and storage. So everybody knows the concept of CCUS, but I think there was a big element missing there. That would be the transportation. So if you go to the EMPP conference a lot, they are now trying to use CCTUS rather than CCUS. This research program has got more and more attention since 2023. In Alberta, we got this Pathway Alliance project. It's kicked off in 2023. So the idea is we're trying to build about 400 kilometer to 650 kilometer of CO2 pipeline, where we pick up all the CO2 alongside the main. The resolution in my computer is very low. The main oil sand upgraders. So we pick up and all the CO2 and then try to storage it near Cold Lake. So where we intend to build a CO2 hub there, storage hub. Now, as you could tell, if we build this whole thing in northeast Alberta, we are facing a very cold atmosphere. And the CO2 pipeline, because we're trying to transport it by pipeline, we would like to compress it, right? So the ideal is we compress it into liquid state, and we can get to that later. Now, well, CO2 itself, if it's dry CO2, it's not corrosive at all. But the problem is you pick up from oil sand upgraders where the CO2 captured has lots of impurity, and including, for example, a bit of water, acetic gas. Then we're gonna face corrosion challenge. Now, to navigate this challenge, we should focus on two things. Well, it's a bit cliche. So corrosion is an interaction between the metal and the environment. So you need to know the environment first, and you also need to get to know what's the current pipeline or pipeline-related component, what they are made of. So the material of construction. And in the end, I think after today, as long as you remember these two concepts, I'm happy. So that's the main message I would like to convey. So in this environment, we're facing CO2 saturated water and water saturated CO2. So that's quite difference. So let's get started. Now, to give you an overview of the environment, the condition. So starting from pressure and temperature, so we plot this CO2 phase diagram with the current operating conditions. So from CO2 injection, CO2 enhanced oil production is an old story in Alberta. So instead of you inject steam, you inject CO2 in downhole and then push the oil out, right? And if you use supercritical CO2, it is a solvent, so you can extract the oil even better. Now for the pipeline, you could tell, so if we look at this, there's a pipeline inlet where we press the CO2 and start transport it. And when along the way, there will be pressure drop, right? So it will have a little bit of pressure drop, and you could tell, so when we start transporting it, it is in supercritical fluid condition. Now, here it is still liquid, but it's a dense phase. It's not a supercritical phase anymore. Now, when we do that, for pipeline transportation, we would like to understand the impurity level. Why? Because the impurity level, along with pressure and temperature, especially when you are near the critical point, you may face separation. So in the beginning, you thought, okay, if it's the ideal case, it is in supercritical fluid condition. But because of other impurities, you may enter into a phase separation. For example, fluid or dense phase, was plus gas phase, and it will be very challenging for the pump operation. Okay, so in general, the operating condition for CO2 pipeline is where we have a bit high pressure over critical point. But as an inlet, we could enter the liquid dense phase. Now, for CO2 injection, the temperature is even higher for the downhole environment, and the pressure is above supercritical point. And for the chemistry, because we are using captured CO2, there will be quite a lot of impurities. Now, to give you an idea, CO2 pipeline is not a brand new, it's not something new. We already have existing pipelines in North America for over half century, I think over 50 years. And as you could tell, the current, except the Norway line, in US, we are mainly working on to dry the CO2, rather than get rid of all the other impurities. Well, the problem is if you dry it compared to you purify the other ones, this one is much cheaper. Now, from my understanding, even for dehydration, it is easy or manageable, even the cost to dry it until 600 ppm. But if you want to dry it even further, it will be very expensive. And another thing for this area is, so we've been doing this work for 4 years, 3 and 4 years. There is no standard. So currently there is no ASTM standard or operation standard for the operator and also for the corrosion researchers to follow. So for example, when you design a corrosion experiment, probably the reviewer or your professor asks you, have you followed the ASTM standard, blah, 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 to do your research. Now, if you work on this area, there is no such standard. There's only one existing recommendation, so this one. This recommendation, they call it the Dynamics project, is established by a European consortium. This specification primarily addresses the gas steam derived from pre-combustion plants to mitigate corrosion, hydrate formation, or some toxicity risk. So now we talked about the environment. Now we get back to the material. The main CO2 pipeline, if we want to repurpose it, then you just look at what's the current natural gas pipeline made of. They are mainly made of API X series, but along the way you're gonna have some metering and pipeline liners. Those are stainless steel or higher chromium contents alloys. And if you go to downhole, so first of all you need to pass that casing pipe, so where you inject it, right? So those are currently common made of P91. Now, if you look at those, those systems, we are mainly looking at a CO2 rich phase. So where you captured it, compressed it, and transporting it. So you are mainly transporting CO2, where you have other impurities other gases as impurities. So water served as an impurity. SOx, NOx, they are all impurity. On the pipeline, it's CO2 rich. But when you go through the downhole area where you purchase CO2 into formation water, so think about how you make carbonized water, sparkling water, is you inject CO2, right, into your water bottle. So in that case, what is the rich phase? So water is a rich phase. So you have a CO2 rich phase transported by pipeline, and in the downhole environment, you have the water rich phase, which is CO2 saturated water phase. So the worst scenario would be water saturated CO2 phase versus CO2 saturated water phase. So that's the main message I would like to convey. So when you look at a research, you want to identify which phase you are working on. Now, to give you a better understanding the difference for the experimental setup. So this one mimics the pipeline. So where we inject CO2 and you have a little bit of water in the bottom, right? It will be extracted into the CO2 rich phase. So the main phase, the main corrosive phase is the CO2. Now for this one, where we're making carbonized water, so we inject CO2 into the water phase. So the corrosion is happening in the water rich phase. This is mimicking the EOR scenario. So pipeline scenario, EOR scenario. Now most of the work we have done so far is for immersion. So we measure the weight loss, we do characterization. And this is one of the example of our benchtop reactor and the CO2, supercritical CO2 pump. I use this to show in general how people do it. But if you are interested in working in this area, do not buy that pump. Very bad. Why? Because the supercritical CO2, you can imagine it's cold, right? Like it can cause dry ice. And then this pipe, the inlet and outlet is only 1/8 inch. So it always has some clogging problem and it is very slow. Now you can also host some preload sample or rotating cage in this to have further some other form of corrosion failure. For example, you can preload it to show if there is a stress cracking failure. Now this is just a high level. So high level, what is the problem? What's the main two type of corrosion in this environment? And which each one corresponding to what scenario in real life. So for example, the pipeline scenario and the EOR scenario. Now, let's look at the first one, the pipeline transportation scenario. Okay, so where we have water and other gases as impurity, the main phase is CO2. It's a liquid CO2. So we look at different type of impurities, testing durations, operating temperature, pressure, and steel types, how all of those factors can affect your steel corrosion. Now, before we walk into this research field, we did a big review paper, and we noticed that for this type, so for the CO2 rich phase, there has been lots of study. And you could tell starting from 2010. After 2010, the research kind of stabilized, right? Draw lots of attention. And my students, they collect all this data and try to clean it. So after my talk, we'll have an expert in machine learning, so I won't talk about this in much, and also not my expertise. So we collected, we don't want to, so basically we collect all the data currently that we have and try to train it. And then we got rid of the less frequent, the less existing. So all of those people study quite a lot. For those, they may just appear like a very small amount. So we don't want to use the less frequent data to train the model. And we noticed that, well, you could tell people have been working on temperature, pressure, H2S, NOx, SOx. H2S and NOx are least studied because they are toxic and it's not very easy to set up in the lab. And you probably don't want your lab mate working on this, right? but water, oxygen, and SO2, they are very frequently studied. And based on the current result, we could tell that SOx and SOx, oxygen, and temperature, they play a more dominant role in determining the corrosion severity. Now, to give you another idea, you could tell, so we plot the impurity ppm and and oxygen ppm. You could see most of the study, they are concentrated in this area. So they are mainly working on 1,000 ppm oxygen with other acidic impurities. Now, in my understanding, this whole box is done in so it's done with the system always have to have water, then have oxygen plus other impurities. Okay. Why we must have water? Because if there's no water, there's no electrolyte. If there's no electrolyte, the ions cannot swing. Now, how water works here is you have water is impurity. Okay, so we are talking about pipeline transportation phenomena. So water is impurity. If it's below the saturation value, it should be ideally dispersed evenly in the CO2 box. But if you have other impurities, they might start to bump into each other and form water molecule. And then water molecule gonna hit on the macro surface and then splash. When they splash, it will form what? Electrolyte layer. That's corrosion 101, right? So if it's, for example, 45 degrees C, 10 megapascal, the water saturation value is about 4,600 ppm. So if we chose 4,000 ppm, which is a little bit below the saturation value, ideally, there should be no irrigation of water. So water molecules are evenly distributed in the CO2 box. So why the other impurity works is when you have other impurities, it will facilitate the water aggregation. So water will form molecules and then splash, form a layer. So just to give you an idea why impurity matters in this system, the reason I put not published here is just to give you a general idea why impurity can influence the water molecules. It's not like I don't want to share. I want you to look at this in cautious because I haven't closely checked this yet. I don't want to share something which might be wrong. We also look at the different impurities by experiment. So those are the simulation results. For corrosion immersion test result, we look at single impurities. So the none refers to you only have water. Okay, so you have CO2, you must have water to have corrosion. If you don't have water, then even though you have other impurities, the damage will be, well, close to nil. Now, we noticed that based on the current results, the NO2 is more aggressive than SO2, more aggressive than H2S, and then oxygen, and then just pure water. But the combination of oxygen with SO2 or other acidic acids are more aggressive because oxygen can oxidize, for example, SO2 to form a stronger acid, sulfuric acid, right? And H2S also, oxygen can react with H2S to form SO2 or acid or sulfuric acid. Now, as I said, the impact of impurities with NOx and H2S are least studied because of their toxicity. Properties. Now, so we talked about impurities. Now let's talk about different type of steels. So because it's going to be high level, so I just summarized what kind of steel types has already been investigated in CO2 rich phase, i.e. the pipeline transportation the scenario. And people have been working on different duration from 1 hour to 150 hours, temperature, pressure. Now, as you could tell, the message I implied is people are although lots of work has been done in the CO2 rich phase, different group, they are working on their own study. They may test it, for example, soak the sample in an autoclave for 10 hours, they report their data. The other group may soak it for 100 hours, then report their data. So they are not comparable, and it's also hard for researchers or new students to follow. And that also echoed my comment in earlier, is we don't have an ASTM standard for us to follow in this area. Now, this work was done by a former master's student. So we got a different type of axial series steels and tested in static, so the autoclave static environment, or we use a rotating cage, or we introduce SO2 and oxygen, some different impurities. Now, as you could tell, if we just have water and you rotate it, the corrosion rate is more, so even just look at the surface morphology is more rough than static one. And of course, if you compare two static one, if we introduce the SO2 and oxygen at a small ppm level, it is more rough. And both the corrosion rate data and surface morphology show the same thing. And then it got us to think that, okay, does this mean rotating always more aggressive than static? And if we introduce impurity, is always more aggressive than, for example, 600 RPM. So when we try to explain this data, we checked other people's publication. So from here, you could tell that when you have a static up until the flow rate, they convert the RPM to millimeter per second. Well, in the beginning, the flow would increase, the corrosion rate increased with flow rate. But if you rotate it even faster, the corrosion rate will start dropping. And so same for this one, then we try to look at the cross section to see what the corrosion layer looks like. You notice that this pattern also agreed with iron sulfide contents. So it is not so. So the conclusion is it's not that simple. It can always explained by their corrosion product layer, the quality of the corrosion product layer, but it doesn't have one unified conclusion yet. Now, and I didn't show much, but there are lots of diverse results. For example, as I said, the 10-hour versus 100-hour result, and even at the same impurity level, different groups shows different data. In my understanding, this part of work, even though tons of, I think over 300 papers has been published in this area, we cannot simply just look at them and follow. One reason we don't have ASTM standard, but we still need to understand why they are different. Now, if I think about it, I think the testing duration is one matter because people tested different duration. The other thing is about this water they introduced. So some group they introduced 10 mil. Some group they introduced, for example, 50 mil at the bottom. And when you introduce acidic gas in this environment, this one will serve as what? As impurity sink, right? Because SO2, H2S, they can all dissolve in here. So we don't know how much in real is left there. So that's why I think the result, even though tons of work has been done in this area, they're diverse and inconsistent. Main reason because of varying consumption rate, varying testing duration, and varying water accumulation at the bottom. So that's a pipeline transportation scenario. We will get into the CO2 rich phase. Then let's get into the water rich phase. I will be a little bit high level on this part, considering the time. So as I said, the other one we are looking at the CO2 rich phase. This one we are looking at a carbonized water. So you purge CO2 into the water and your sample is soaked in water. This is mimicking the underground storage or your phase. So same for this one. Back 4 years ago, not much people has been working on this area. So the data I showed it for this scenario is mainly from my group. We did work on different testing duration, temperature, aqueous chemistry, and also chromium level, as you could tell. We soak the sample in water-rich phase, it will be more aggressive than the other one, right? So we're not looking at the pipeline still anymore. We should have introduced some chromium contents into the steel to try to be more protective. Now the first one we showed is a testing duration. As you could tell, if you calculate the corrosion rate from a longer immersion duration, the corrosion rate will decrease. Why? Because over time, your corrosion product layer will grow and cover the surface and slow down the kinetics, right? So if you compare your 100-hour data with other people's 10-hour or 1-hour data, well, it will show like even a magnitude difference. So in reality, if we tested a very short time, we may overestimate. And if you use a result for a very long duration in static environment, you may underestimate it. Why? Because in reality, system is not static, right? So here you just soak the sample in this environment. There is no erosion or no flushing or no rotating. So it has least possibility to damage the protective layer you formed here. Now on the other side, so this is we tested for different duration. We also tested for different temperature and pressure. In my mind, I thought when you increase the pressure of that water pump, the corrosion would be worse, right? So compared to room temperature versus 100 degrees C, 100 degrees C would be worse. And if I soak this in DI water, so no other chemicals, versus if I soaked it in seawater, let's see, 3.5 weight % of sodium chloride, then sodium chloride solution should be more corrosive than DI water. That's, when we design the experiment, we already expect the result or the tendency at least. But when we look at it, it's the opposite. Okay. So for example, first of all, let's look at just so this 50 means the pound of water is 50 degrees C. This is DI water. This is sodium chloride water. If we just look at this two, you could tell sodium chloride corrosion rate is way smaller than the DI water one. Now, when we look at this one, so if it's just sodium chloride solution and we increase the temperature, now we're all talking about statics, that's why I say we may underestimate things. When we increase the temperature, the corrosion rate decreases. So it's the opposite of what we expect. And then I say, okay, when my student present this data to me, I said, repeat it. Okay, I don't want to present something and then looks like an idiot. And then they repeated everything that it's the same. And then we got back to see the compact layer, the iron carbonate layer formed in this environment. Apparently, when you have sodium chloride versus DI water, you have a more compact and more dense layer. Same for the temperature. When you increase the temperature, your layer formed very quickly and also more compact. Now, I'm not an expert in simulation to understand this, but over the years, we did some DFT calculation. Now, we had that editor a seminar talking about it. Years ago, if you want to publish in Corrosion Science, okay, if you just present SEM, regular XRD, no, not good. Even though you can explain it, they still want to see the fancy TEM. So these days, if you want to publish it, you look at all of those. Even though the DFT just give you a number, they still want to see. So they look at the paper. When we quickly review the paper, you have SEM, you have TEM, not good enough. You must have some simulation result. So I can find this annoying, but at least for this point, they help me understand why. So why sodium chloride solution is least corrosive compared to DI water. So when you have chloride, the iron carbonate absorption is much easier compared to there is no chloride. So they can quickly form the layer. So it all goes back to how we can explain the corrosion rate. It can be explained by the quality of the corrosion product layer. So that's a chloride effect. And on the other side, so we are injecting CO2 in the formation water or in the DI water, right? But there must be a solubility. So with sodium chloride, the CO2 solubility is way smaller than compared to DI water. So you have less CO2 forming carbonic acid. So the pH is higher. So if you compare this one, so this line is a DI water line, this is a brine water line, right? So the solubility of CO2 is much smaller in brine water. And as you could tell, with increased temperature, the solubility of CO2, so there are less CO2 forming acid in that carbonized water. And the temperature can, so at the lower temperature, the nucleation of iron carbonate, the product layer, primarily governs the initial formation. And they followed by a relatively slow growth rate. So we'll have those bumping porous side. But if you look at the relatively higher temperature, they have a lower nucleation rate, but they grow very fast. So they cover the surface rapidly. So that explains overall. The next part is we try to focus on different chromium level. Now, I think it was 2024 when we go to EMPP New Orleans conference. They were asking what kind of grade can be safely used in this scenario, in the water-rich phase scenario. And most of people are trying to say, are we going to be crazy to use stainless steel or a lower chromium level? So we did a series of chromium level from X80, which is a pipeline grade, to increase to 2 chromium, 5 chromium, P91, and 316, and even crazier 800. We noticed that at least you need to use P91. Well, most of the good thing is most of the current casing steel, they are using P91. I don't want to go more detail in this area. So this 3 alloy we present here follow this monotrend. So you increase chromium, it decrease. The reality is it is not. but that will be a whole different story we will talk about. I won't cover it today. So it is not that simple. Now, after this, we did just regular characterization, and then we got rejected. Well, the story doesn't change at all. We got rejected. We add on TM, we got accepted. So you see how annoying they are. So from why P91, starting P91 works is if you look at the number 2 here from P91 and the number 4 here for stainless steel, they form intermediate chromium rich layer. So there will be another intermediate layer or transition layer to protect it further. So when the chromium contains above 98%. Now here, so let's read. This is all about the carbonized water. So the water-rich phase where you inject CO2 into the water versus the previously we talked about the CO2-rich phase. So as I said, as long as you remember the difference of these two scenarios, it's already good. Now the key aspect is the CCTUS are carried out under supercritical state or dense, at least dense CO2 phase. This area do face some severe corrosion scenario, and it worth to explore if you're interested. And there are two different scenarios. One is a CO2 rich phase. The other one is CO2 saturated water phase. Now, from this, you could tell there are lots of factors. Okay, the experiment is hard to work. It's not like you have a glass cell. Let's do it. So it needs it needs a supercritical fluid pump. It needs different kind of impurity gas lines. So it is expensive to run those tests as well. So what we are promoting is we try to work with machine learning colleagues to accelerate this by training our existing data and use that data as a feeding, as an input. So hopefully with machine learning's help, we can accelerate this approach and also we support this industry. Okay, great. Thank you. Question?
Yes, we do have some time for questions, right?
Yeah.
9. Yes. Good. So oh, no, I have a lot, but please, some question?
No, it's okay if you have lots of questions.
I start.
Yes.
So with the P91, you said it looked like the chromium increase would help, but then you said in reality it's not.
So yes, with higher chromium, it definitely works, but it's more expensive.
Mm-hmm.
In reality, it's not, as we have another study, it's currently under review, and I'm looking for criticism. So about P91, so from P91, it is, when you increase chromium, it will decrease the corrosion rate. The difference happened when we have when we have less than 5%, 5% of the chromium. So from 2 chromium to P110, which is 1 chromium, and also the X80. So those rates, we found something interesting result. They are not like this.
Because there has been this debate also in the other localized corrosion community that you need at least 11%, and 9% is close to it, right? So in order for the chromium to form a full network on the surface, so maybe if you go lower, it might even be detrimental.
Yeah.
So maybe that is what you're seeing.
Yes and no. The thing we noticed is the intermediate layer. So the corrosion rate will decide. Well, yes, you're right. It depends on what kind of intermediate layer we're gonna form.
Right.
So it might not be just chromium oxide. It might be because you eat lots of iron out first, and you left some other phase. For example, iron 3 carbon. So iron carbide.
Yeah, cementite. Yeah.
Cementite. Yes.
Yeah. That makes sense. And then the chromium cannot be protective, but it still hinders the iron. The other. Yeah.
I think it will also help if we can design an electrochemical cell for this environment. As you could tell, it's very challenging because of pressure. It's not so about the temperature; it's the pressure. Pressure is like currently we are mainly focusing on just 8 megapascal, 10 megapascal. So I don't have such a cell yet, but hopefully we do. I know people from, I think from Norway or Denmark, I forgot that they have that they have that a quartz window. They could see it for the CO2 study. Right. Yeah.
Is that's for the supercritical?
Yeah, CO2. I think they for that those quartz window you could tell, and they also do electrochemical testing.
Actually, it's Estonia.
Estonia?
Yeah. I think they have one, and then there's some guy on YouTube that ended up doing a video of the whole thing. And they have one at the museum, and then one is like given to him, I think.
Yeah. So it's like a portable one. When you charge it, you could see the face changing. And then if you put a metal coupon inside it, you could see it. That will also be very useful if we go to the Canadian light source to see, if you use synchrotron to see the basically XRD, so strong XRD phase. Yes.
Sean, I guess the chemistry of supercritical CO2 is, it is kind of in this mixed phase of gaseous and liquid at the same time. How does that affect corrosion? Is there polar molecules still going on with the impurities, or how does supercritical fluid act as a base for your water impurities?
Now I think for us, for our study is we first just clean the system and then purge the CO2. So the CO2 will from gas to dense phase and then to supercritical. So it is pulling the impurity in it. So if you have a small layer of water in the bottom, and of course, if you think about the environment, it's very vibrant, right? It's not, even though we say static, it just means there's no mechanical rotating. But I think they are pulling the impurity out into it. And when it reaches supercritical CO2, it's pulling even more. So we do have another study working on calculating the water solubility in CO2 phase from gas phase to liquid phase to supercritical phase. And when you have enough water, it can dissolve the acidic gas. The other thing is, I think because we cannot see it, it's just my estimation.
Right. So I guess it kind of acts like a vacuum, right? You have a vacuum chamber.
Yes.
Comes up through the walls and makes out fluid. But I guess because CO2, it has, I guess it's just more solid, more active or whatever. It will pull all those molecules off the walls into your thing. So it just makes it so much harder to make those materials or clean those materials. You have to be almost vacuum safe when you're making pipelines.
Yeah.
Get those impurities out of the walls.
Yeah.
So you don't run into this.
I think there is another group in our university from civil engineering, Charlie Jin. They are working on calculating the thermodynamic property of CO2, and they calculate, for example, the phase envelope when you introduce different impurities. So they are working on that part, more on the CO2 part.
Kind of like a TG where you see this like massive.
Yeah. So in the beginning, so if there is no phase separation, you have a line, right?
Yeah.
And then if you introduce impurity and different impurity, then this line becomes to open like a crack. So that's a phase envelope. I haven't touched on that because that's not my expertise. But we are working together because in my mind, as I said, I cannot see it. It's when I explain the result, it's more estimation. Yeah.
Still trying to wrap my head a bit, like what is different between liquid CO2 and supercritical CO2?
Liquid CO2, you could just say it's a dense phase, like it is liquid, but supercritical CO2 is more, it's even denser, but it's act like a solvent. So it acts like a solvent, but how to say it? It's a difference.
So it's kind of similar
To what? Supercritical water.
Yeah.
When I look at it, I also check that to video. So when I notice it's gas and it's liquid, and then it kind of like oily. When I look at the texture, it kind of like oily.
Yeah.
Yeah.
Yeah, and like.
Thank you.
Well, I was just wondering, thank you for your talk. I wanted to ask about your samples themselves. So, obviously this is going to be a pipeline. I was wondering if you looked into any texture effects.
We haven't.
Not yet.
Yeah, that's a good point. Yeah.
Because you're operating at 10 megapascal. It's not at the same level, because we're nuclear. Just looking at pressure tube, for instance, where like it's 15 megapascal for the CANDU pressure tubes.
For the CANDU one.
Right. That's 10. So about the same pressure then, which is great. So we actively want texture, obviously in the zirconium too. So I was wondering if you had looked into texture yet, because I know.
No, we haven't. We haven't checked. We just fine polish it at this point. We didn't work on that one yet. Great. I also worked on
another question here while we are setting up. So sodium chloride, does that increase the risk for stress corrosion cracking? Or by like starting with pitting and then?
Yeah, I would think so. We haven't published that one yet, but we did. So we have a preloading sample. That's why I always say that we underestimated because it's kind of static. Yes. Well, the short answer is yes.
Thank you so much.
Thank you.
Wait, you get a gift.
Oh, I get a gift. Oh, that's good. Oh, thank you.
Can we have an applause? Oh, and then I can introduce the next speaker. So Professor Tian is an assistant professor in the Department of Chemical and Materials Engineering in the University of Alberta, specializing in the development of machine learning, accelerated simulation methods for interfacial materials design. And we will hear about machine learning now. So yeah, I'll get you the mic. Here.
So do I need to
Yes, you do need to go to the Zoom and share. Is it okay, Nagis? Yes, good.
Hey, good morning, everyone. So I'll be continuing on Dr. Liu's talk about. So she's mentioning about there was many of the applications that we wanted to have AI and machine learning for corrosion prediction and integrity. So what kind of problems can we actually use AI machine learning for corrosion prediction and integrity and prevention, and how are we actually dealing with the machine learning? What are the topics that the literature is talking about for machine learning? So these will be the main topic about my part. So on the record, I'm not, say, originally working on the corrosion field. So many of the concepts I might be taking from some other, say, interfacial phenomena. So correct me if you feel like some of the time you think, yeah, this guy is just blowing too much. But hopefully I will get the scientific part correct. So about myself, I did my PhD in etheospheric, and I did a postdoc in Carnegie Mellon and also Georgia Tech, working on different perspectives about applying machine learning on molecular simulations. And I joined University of Alberta last year in CME, and I'm also ME fellow at the Alberta Machine Intelligence Institute, and recently got nominated for the CIFA chair. So in our group, what we are mostly interested in doing the research is machine learning accelerated interface simulations. So two of the scientists I like the most are the two gentlemen on the right-hand side of the screen. They're actually very different personalities. Actually, the two extreme spectrum ends of the spectrum, but in the case of Wolfgang Pauli, who is actually also I would call say one of our previous colleagues in etheospheric, we also even have a name of we even have a street named after him directly just a bit behind our building. So he says God made the bulk, the surface was invented by the devil, which means that in the 1920s people have already been studying using say the theories of atoms to do any simulations. At the time, it's really easy to say format any of the what we call now is the descriptors to describe any of these molecular or atomistic systems. But when you want to do the simulation on the surface, so when two or more materials are combining together, in the case of a corrosion, this is a solid surface, which could be alloy or pure steel, and the other phase is a liquid plus any of the gas or the impurities. And the surface is actually something very difficult to model. One thing is that you have to include all the atoms into the simulations, and the other thing is many of these simulations, they are also having so many configurations that can happen. So think about that. You have different types of a surface, different elements, arrangement on the surface, and also what are the neighboring gas phases on these surfaces. So they're intrinsically hard to simulate, but once we get every single knowledge about these interfaces, we are potentially able to answer a lot of our questions. So the second gentleman, Richard Feynman, says that there is plenty of room at the bottom. So if you are going to have a way to control how the surfaces are, say, built up, or you can know where the say active sites on the surface actually lies, you can make many of the interesting applications. So in the case of corrosion science, I think we wanted to see how the length scale matters. So this is taken from my previous research regime, but I think the same analog applies here. So usually when we talk about any material system, we are almost following the diagonal line. Like if you are going to maybe study any system with the electronic structures, you will go to the quantum mechanical way, but you are limited on studying at the range of several angstrom to nanometer range. And if you're going to do something with a larger scale, like fluid dynamic simulation or the finite element simulations, you are limited by the time scale that you're going to be able to do in these cases. So what AI and machine learning can actually help in these cases are actually you can have your system which are built onto the atomistic scale, But because the AI and machine learning, if they're trained well, they can create the different configurations much faster than the originally say physical method. So you can increase the complexity of these systems. So the hope is that with the AI and machine learning, you can hopefully bridge the gap between different scales in these simulations, which I'll be covering in the later part of the topic. So my group is interested in material simulation, and this is some of the slides I usually use. That for Canada, this is actually very say a critical problem because if you think about the major applications in Canada, we have a critical mineral efficient catalyst in oil and gas industry, and we are here that at least 1/4 of the problem will be lying into the pipeline materials, and this is where the corrosion needs to be say considered well. But of course, we have many other things like a battery and say storage materials that are also very important. But I would like to say that corrosion is a quite important topic, and you'll find out in the later part of this topic that applying machine learning onto other fields kind of seems like a well-knowledged case, but in the case of corrosion, I think it's just started, and there were some interesting reasons for that. So the first question about corrosion is, what kind of scale is the corrosion problem that we are going to be studying? So let's forget about the middle ground here. The left side will be about corrosion integrity and prevention. So if you are going to set up a pipeline which takes about a few hundreds of kilometers to transport from one side to the other, you potentially can have some sensors to put onto the pipeline, or even nowadays you can have automatic say imaging application onto the different sides of the pipeline, so you can take images to see where the corrosion happened, and you can build image set on top of that. So basically, you are measuring how long should I wait until to replace the pipeline, and on average, what is the corrosion rate at the millimeter per year. On the other spectrum, in the lab research, we as material scientists usually do so-called corrosion simulations. Basically, this is to put different atoms onto different surfaces and try to study the energy and the different say pathways of the possible reactions. So these two streams, I think we have seen applications of machine learning onto the two ends. I think the missing part is also how can we bridge them together. So let's first talk about the first part about corrosion integrity and prevention. When we are talking about applying machine learning to any of the problem, I think this will be the main takeaway message from today's talk. So I would like to think about any machine learning or AI approach like a black box. So when you construct any say a machine learning algorithm or code or whatever, think about that the model and algorithm is a black box. Usually when you design following the logic, you will first select what input and so this input feeds into the model then goes on to predict your property. So logical flow is from 1 and 2 and 3, but in reality, what most of the time we are doing is we are going to first define what is the property or the label that we are going to study, whether it's a corrosion rate, the bit depth, or the remaining life, or in some cases you can have a time series prediction, like if I have this system and I have measured the corrosion rate at 2 hours to be something, what is the potential corrosion rate at 8 hours from now? And secondly, you will try to design the so-called input or the feature. So the input and feature in the more macroscopic way could be what is my alloy composition. This could be taken from all the elements, element composition from your alloy, or it could be from a machine learning perspective, it could even be just a name of your steel if you want to use that one as the input. But of course, we are doing something in the feature space. You can add the experimental conditions into the feature space, and now you can say distinguish between whether these say features are first principle. By saying first principle, these does not need to be measured. So if I'm going to use any other material, like I take another pipeline, steel, alloy, I can directly use that composition to feed your data. And some of the quantities need to be measured, like they need to first measure the thermodynamic quantity of some of the materials. And we are also interested in what is the data size and how large the feature domain size. And the least important thing I would say in the machine learning is actually the middle step. So choosing a model and algorithm is typically something that you want to design in the last step, because I can show you in the later case there is some correlation between your input and your model size in the heuristic selection rule. So for the next few minutes, I will be talking about how is the machine learning currently used in corrosion literature. So we'll be interested to see what kind of subdomain in corrosion science has been using AI and machine learning. What kind of problems? So what kind of approaches can be used to study the corrosion problem, and how are these input and outputs defined? And most importantly, we want to also see are these models phenomenological or mechanistic? So are they going to be just some artifacts about the machine learning, or we can get some insights from these models? So to be able to do that, we in the lab are building a language model-based literature curation workflow. So this is slightly different from a machine learning perspective, but basically as we are trying out something that we are writing the codes that can access the database and to search for different literatures and to extract the different paths from that literature. And then we build an agentic language model layer on top of that. So when a lab student or a researcher wants to, say, study these problems, the search can be simply a combination between user selection and the user prompt. So for example, the field slide I'm showing afterwards is basically I'm just asking, I want to identify the literature of machine learning usage in corrosion science. And after some iterations, we are creating about 260 journal articles. So during the cycle, the language model are going to select the literature that are similar to the criteria that we're defining, and we are using the extraction from these data. So what kind of corrosion subdomains have adopted AI and machine learning? Most likely you will see three big categories. We have a pipeline, a marine corrosion, which is similar to pipeline but more onto a saline say environment. And another big topic is to design different say corrosion resistant materials. So the left-hand side is most about if I have an in-field condition and other sensor parameter, can I build a model to predict the corrosion rate and other say and other kind of say properties. On the right-hand side, the corrosion resistant material design are mostly say trying out different materials in a lab to fit a model that can say predict the corrosion rate on top of those. And we also did say analysis about what kind of models are currently used. So if you are going to see the names, they are actually very say close. That you will very frequently see that they are either say regression model or classification model. They have a machine learning. They are having feature engineering. Some of the interesting thing is that we do see image analysis on top. Say in these applications, mostly they are in-field say study that using computer vision to see which part of the application or the pipeline is corroded. Yeah. So we also did a study about what kind of machine learning models are frequently used, and more than half of the model actually clustered about the top 1, 2, 3, 4, 5, 6. So 6 different methods, and in the last one you can see that this is basically just a linear regression with some better regularization. So the baseline is linear regression, but usually people use some better ways to do the regression test. And you can see that the most well-adapted one, apart from the neural network, is the random forest support vector machine and gradient boost, which is a type of say ensemble model and decision tree as well. So I would say that if you look into the name, the names are not that much important. As I said, the model themselves, you can treat them like a black box. The definition of the models may matter about how robust these models are, but you can treat that most of these models are the default model to use, so you can actually just when you prepare the input and output data, these models will be the baseline that you can directly try out. We do see some interesting tasks that will be not covering discussion today, that you do have the convolutional neural network, which are a set of computer vision models. So they are mostly supporting the industrial surveillance applications. And some of the works also included the time series prediction. And I think this is something maybe more important in the future years as new data are going to be added into the data set. We then can be more confident about asking a question: if we have corrosion rate prediction, do we directly take the first point, or do we take something like 128 hours, or do we use a time series prediction to do the whole series with other multi-domain data that put into side? But I think I'll be just skipping this part because it's probably too much information. Something I think more important to see is the dataset size. So I did analysis about the dataset size in different say sub-domains in corrosion science, and respectively with their say trained data size. And you can see that except the final row that we have computer vision and imaging dataset, so these applications might see the datasets to be more than 10,000 or even approaching 500,000, because taking a picture can actually be very cheap, and you can do it collect say a few months of data as a training and to just train that. But most of the other applications, if you think about how you do a corrosion experiment in a lab, you prepare the sample, the different conditions, and you measure the rate. It's probably harder to accumulate more than a few hundred of data sets, not to mention to accumulate something like a 1,000 data set. So we see the majority of our data sets here say lying below the 1,000, say 1,000 mark. So we can more or less say that the majority of the corrosion machine learning applications have a so-called small data set, say range. So when we talk about dataset size, from a machine learning perspective, there is actually a very good way to select what kind of models you want to use. So this is taken from a package called scikit-learn. If you are using Python to write your machine learning applications, this is potentially your first point of contact. So you will, if you ask any of the language models to write a script for you, they will probably give you a scikit-learn say script. If it's not, then it's probably not a good language model, so you can discard it. So the way that we see this workflow is, let's say that we are interested in going to do regression. The regression is, if I give you the input, I want to predict what is the corrosion rate as the continuous variable. So let's go with the start. So if we are going to see, the first thing is, do we have, maybe from the audience it's harder to see, but I can say that, do we have more than 50 samples? If no, then try to collect more data and then apply the machine learning application afterwards, because it's probably not sufficient to say that you are applying machine learning. So after that, let's see if we are going to be a category, say problem or regression problem. So categorical problem is if you are going to say, I don't want to predict the corrosion rate, I want to study the corrosion criteria, whether it's good performance or bad performance. You can go to classification approach. But from my perspective, if it's a continuous variable like the corrosion rate, you just go to regression. So now you go to regression. Do we have more than 100,000 data set? Most of likely no. So we want to go from this branch. And now the question is, what kind of features do we select? So the feature in the most natural way is you collect what, say, composition of your material, what are the experimental value, experimental conditions to be a tabulated table. And then we ask the question, are all the features important for your study? Let's say that we have 20 different parameters that we want to do the fitting. If all the 20s are probably going to be important, we go with this branch. That we either go with say the SVR, so the usual kernel method support vector machine regression. And in some cases, it's also worth to try different ensemble model like the random forest and XGBoost. So most of these methods are actually the one that we are showing in the last slide. So if you see these, the SVM, SVR are the kernel method that they recommend. And by comparison, you could also go with random forest and XGBoost, and they're on par with the same results. So that is the reason why you, if you're going to see any of these machine learning papers, these 3 or 4 methods are just a jump out of the context, because this is the way that these smaller data sets should use the models. Now, on the other side, some other interesting problem we also see in other data sets is if you are interested in to have some of the features taken from a data set, but not all of them, you potentially can use more robust method like lasso regression to select the subsets of your say feature space to predict the problem, or even using some more fancy thing like symbolic regression. So we have input quantities, and I want to study a different arithmetic combination of your quantity to be descriptive, but that's another story. So yeah, we have known that we don't need to compare every model for every problem. Potentially, if you have say a slice of your data set, we can choose something from this chart to do. Unless you have a really large data set, so SGD regressor is say just a very broad term enveloping all the neural network models. So we want to just show one example that if you see any paper that talks about machine learning for corrosion, you can talk to your colleague like a Prof. What exactly is this paper talking about? So just to take one example that I'm just asking my language model to say, yeah, let's pick out one machine learning study that has the highest citation and also something that you can rank as the likely true study. So yeah, this is the one that we selected, which is the feature selection paper about the corrosion, I think in a marine environment about low alloy steel. So what are we looking into this? What kind of information do we need to look into this paper? Most likely, let's still go to use the black box analog for a checklist. So what kind of problem do we study? It's easy to search for this paper that it's predicting the corrosion rate for low alloy steel. And what are the inputs in this paper? So in this paper, they are combining both the material features. So alloy composition, but instead of directly using alloy composition, they are using some arithmetic combination of the alloy composition to just make the feature space larger, and also include the experimental conditions in these data sets. Outputs are easy to define, so this is the corrosion rate in millimeters per year. The models that use, you can search that it's a random forest with some say feature importance that output afterwards. So this paper is about so-called feature engineering. Basically, when you see the feature engineering, this is talking about that if you have different features, you can use say the internal weights from these models to tell you what kind of features are most important for your application, and do we have a feature correlation between each other. So feature importance figures are easy to understand. Usually just look into the say histogram bar that maybe for this application they are having some thermodynamic quantities that are more important than the other. The feature correlation image sometimes are say underestimated in most of the papers, but one thing I wanted the audience to notice is that to see if the feature correlation space does have many highly correlated sub-features. So for this example, they want to show that many of the blocks in this correlation matrix are actually either +1 or -1. So they are directly correlated. So they are actually redundant experimental variable. You just need one of them to do the regression. If you use two of them, it's probably going to be a waste of a feature space dimension. So yeah, so that's a good part about seeing a paper. Something that you probably will take a grain of salt to read the papers like this is see that this paper has 85 calculated data, and we are asking ourselves the 50 is probably the criteria that you want to say distinguish between something you do with collecting more data and applying machine learning model. So whenever you are reading paper like this, the first question is could the result be overestimated or underestimated during the these reported values. So something in machine learning that can be overseen is that many of the cases for smaller data set we are using things called cross validation. So you rotate a different split between your test and training and test data sets. So some of the reporting results may have contaminated the test results to actually see that data before. And the next question is, does the model generalize to other systems? For this paper, the model is kind of possible to be generalized because they are designing the feature space to be some combination of composition. So hopefully, if you take other alloys into the system, you can directly use the same formula to test. And they actually show that one example with unsteamed material with a nickel-containing steel. And can we obtain the mechanistic insights? I think this is a difficult question. We do have the feature importance in these kind of papers, but feature importance really matters about what kind of a model you are training on to. So that's something we should always take a grain of salt. Like for the smaller data set, this is probably something confined to that data set alone, and without actually seeing the symbolic regressions, this is probably something we shouldn't take too much grain of. So think about that problem. One of the things me and my students come up with is many of these applications in of machine learning in corrosion science is actually about you collect one data for your one example, and you are going to apply a machine learning model for your in-house data, which most of the cases they should work well because you can always find a feature space that fits your model, and they may be working also for your setup. But what about if we do want something that is more transferable, like Dr. Liu has talked about, you have, water in supercritical CO2 corrosion and CO2 in aqueous solution corrosion problems. So there are many literatures out there for the data. And now the thing is, can we use these, say, systematic literature data to do some prediction? If you still remember, we are actually doing the literature review on the language model study level. We actually can do the same thing for creation of the data. So we did the same thing that we do human plus the prompt creation, and we use the language model to do the pre-screening for us. Say, is this the relevant data, and this one has a relevant corrosion rate figure. We use multimodal information extraction to analyze these data to curate a tabulated data set. But most interestingly, instead of directly having a model that has the input, you tell me what is the corrosion rate output. We wanted to use something that has the uncertainty directly to be embedded into the model. So the work has been led by my master student, Prince Etiano, and in collaboration with Dr. Liu as well. So we want to see that if on a test set, can we directly know not only the predicted value, but also from the literature what is uncertainty about all these values. So Prince has tested out that if you are going to use a Gaussian process on the literature data set, so he has curated some, say, manually curated data sets onto these, and the Gaussian process actually works at least on par or better than other kind of models. So another thing that the Gaussian process model can tell you is that if you are going to predict the corrosion rate of your, say, aqueous CO2 corrosion, it has an error bar about the predictions. And the error bar is not coming from, the error bar itself is not coming from some other quantity, but actually this is to be measuring if the current literature has more data on this input side. So we probably have more samples on the high rate corrosion side because this is aqueous corrosion, and we have less data on the lower rate corrosion side. So this kind of model can actually tell you that if you are having a new system, the error bar in this prediction will work as, say, some estimation for your new experimental setup. And you can use this model as your, say, some first of contact model to design the next experiment. So the second part I want to briefly talk about is about the atomistic simulation part in the corrosion, so in the machine learning application in the corrosion science. So when we talk about the atomistic simulation in corrosion science, we basically wanted to see if we can directly see the atomic events on the system, like in the CO2 corrosion of alloys. So still we want to use the black box analog for us. Like if you have the automated simulation, what type of models are you using will be in the black box. But we are interested in see the input and output. So different from the macroscopic studies, the atomistic input are actually directly the positions of the atom. So almost no other information should be given. And the output could be the energy differences if you are studying a reaction, or the kinetic rates if you already know what is the transition barrier of your say, reaction. So basically there are two different ways of doing these simulations. The first one is the quantum chemistry way of doing simulation using density functional theory. If you think about it in the black box way, this is you construct different structures like A and B and C and D to represent your local environment in your chromium containing alloy, and you add the different CO2 into different compositions and calculate the energy for each of them. Every single structure will give you absorption energy of the CO2, and you can compare if the current binding site for the CO2 is strong or is chromium serving as the active sites in the alloy. So this is a very accurate method to calculate the energy, but very expensive. So to be able to answer each single frame, usually you need a total of 10 to the power of 2 to 10 to the power of 3 CPU cores. Now on the current supercomputer, this is not a very heavy load, but if you compare with the second method, the molecular dynamic simulation, this can be actually quite expensive. So molecular dynamic simulation is in the corrosion perspective. People are interested in to see that if you just cluster a bunch of CO2 atoms into the chromium-containing iron, chromium-containing alloy, that's the CO2 land on the surface and nucleate with the metals inside. So they want to find out does the nucleus grow in what kind of format. In the molecular dynamic simulation, you can typically go beyond several hundreds of picoseconds or even 1 nanosecond if you want to go further. And on today's supercomputer, this is easy to go beyond 1 nanosecond per day for any of these simulations. But the next question is, most of these simulations are done on, so the parameters for doing these simulations are taken from other systems. So can we fully trust these parameters? Because they are, like the machine learning, they are having some uncertainty. So we are not 100% sure if the molecular dynamic simulations are actually fully correct. So in the field, there has been a lot of effort to be using the machine learning to be able to predict something with the accuracy of a density functional theory, but also fast enough to work with the molecular dynamic simulation. But there are two challenges currently facing. So first one is, like the feature in engineering, we have the structure embedding. What kind of data should my atomic structure give the model? Is it directly coordinate or something work on top of coordinate? And second challenge is, in the field, there are indeed some foundational or large models that train on different type of systems like battery, catalyst. Can we directly use these models to predict things in other applications like corrosion? So these will be the open questions. I think hopefully by the time of 2026, we can more confidently say that these two, at least there are many progresses in these two directions. So the first thing is, how do we represent the atoms into the machine learning model? People actually are thinking about if your input is anyway the atom structure, maybe the feature that we also give the model should also be on top of the atoms. So the majority of the way is to using graph neural network, so representing the atoms like a graph nodes and edges to be inserted into the machine learning model. From the very beginning of 2018, we have this crystal graph collisional neural network that works well for bulk materials, but not for the interfacial materials. And people have been applying different techniques for studying the interfacial representation. And the current benchmark is this maze model that you can almost take it as a black box model to be applying for battery predictions and other things. And the other type is we do have larger data set in the atomistic simulation, much larger than the macro scale corrosion data sets. So our previous group has developed several versions of the open catalyst data set, ranging from the metal to metal oxides to last year, also including the solvent information. So basically, these are just some random structure calculated on the density functional theory and thrown onto some graph neural network model to be predicting the energy output. And if you are going to train the newest version of the maze model, like I said, you can indeed simulate a pretty good Poivet diagram about any of the metallic system. So this is a good thing about directly using the foundational model to do the predictions. But we are also seeing the different, say, challenges because we do have a lot of outliers in the test data. that they are having an energy difference with the predicted. So the DFT with the predicted value is more than 1 eV. And if you think about you are going to be studying kinetics, this energy difference can be actually astronomically large. And this is not only to just throw more data into a larger model. From the analysis of the historical model growth, we have seen that in the first few years, these models have been gradually improving a lot, but somehow plateaued around 2024. So you need to probably throw 2 orders of magnitude of new data into the system to be able to improve the accuracy. So do we need to wait another 10 years until the models are improving, or can we directly use them right now to do some realistic simulations? Some of the way that we have been proposing to use is we can use the so-called multi-fidelity hybrid simulations to overcome this challenge. So because of the time limitation, we still want to think about this thing as a black box. But instead of directly using everything in the pure DFT or everything in the pure machine learning, we do have an iterative loop that for highly uncertainty region, we use DFT to get the data, and these data were going to retrain the model to be able to get much faster results to the final conclusion. So one of the examples that we can do is if you're going to study a very difficult absorption energy simulation, the left-hand side is using a pure DFT relaxation. The atom is moving very slow on the surface, and each time frame is a very expensive calculation. On the right-hand side, we have this hybrid relaxation scheme. So because the machine learning can explore much faster and even into some, say, slightly distorted geometry, it's actually making the discovery of relaxed state much faster than purely using DFT relaxation. So you can almost say that on the right-hand side, you can reach the ground truth 10 times faster than the left-hand side. And you are also guaranteeing the final result about this absorption energy is fully correct. So to be able to use this kind of a technique, we indeed develop a few computational softwares that can be combining say the legacy quantum chemistry codes to the machine learning models. So if you're interested, we can have a discussion about how applying these things into your existing problems. So currently I have 2 students working on how to bring these machine learning tools to be more entry-level friendly. So in the last 1 or 2 minutes, I'm just thinking more broadly, like, yes, we do have a 2 spectrum, like macroscopic corrosion. Even if the data sets are not that much big, we do have knowledge that using data set compatible machine learning models can guarantee you some good results. In atomistic simulation, we are having machine learning accelerated frameworks to get you some answer about energetic results. So the question is, how do we combine these 2 things together? I think in the next few years, we need to actually actively bridge these 2 regimes together. So from the macroscopic corrosion phenomena, from a certain system, you should be asking the atomic simulation to generate the different, say, representative systems to compare the energies that you are outputting. And from atomistic simulation events, we do need some sort of a so-called knowledge distillation. So to combining the results from atomic simulation events to something that is more explainable in the macroscopic phenomenon. One thing that I think eventually what I want to mention is if you think about the corrosion rate in millimeters per year, and you convert that one to how many atomic layers I can remove per nanosecond. So nanosecond is a typical time scale for the molecular dynamics simulation. And if you compare these 2 time scales, you see that a corrosion rate of about 1 millimeter per year is actually just a 10 to the power of minus 10 nanometer per nanosecond. So basically it means that you can never see the real corrosion event in the molecular dynamics simulation. So these events are actually a rare event-driven scenario. Unless you do a lot of, say, configurational space searching and atomistic events, we are not able to fully, say, answer these questions. without combining these two regimes together. So I think the take-home message for today's topic, is that I gave a very high-level overview about what kind of machine learning, say, approaches can be applied for corrosion, say, studies. And when you're looking to study about ML for corrosion, what key information should you identify from these literatures? And I think the next step is to have uncertainty power model and also on a larger community data set to be able to fully understand these questions. Thank you.
Thank you so much. Because of time limitations, we are cutting into the coffee break, and I really don't like that. We please ask your questions during the coffee break and in the chat. And there are a lot of questions in the chat also for Jing. So if you could have a look, maybe then you can answer them there. And for the next speaker, Shiva, maybe it would be good to set up, and we can start that 5 minutes over, so we get a little bit more coffee. Okay? Thank you so much. And this is a big one. It's funny, I can't see the